All right, guys, welcome back to Statistics after spring break here on April, I don't even know, 15th? 14th? 14th sounds good. We'll run with that. So what we're going to do is we're jumping back into sampling distributions. Now, if you have forgotten a little bit about sampling distributions, we are going to talk about them in this video, but you can always check out the videos from last week. Just as a little bit of a refresher since it has been a bit of time. But we are going to do a couple of problems on your packet. Now this is the very first page of the packet, the very front of it. And we're going to look at question 5. Question 5 says, according to the Red Cross, about 42% of Americans have type A blood. Suppose 80 people show up at a typical blood drive. What's the expected proportion of people who are type A? And what is the standard deviation of a type A proportion found at such drives? So what we want to do is we want to create a sampling distribution for this data. Now, to do that, we draw a normal distribution. I mean, technically, you don't actually got to draw this stuff, right? Like, you can just kind of think about it. But for the sake of showing this off, I'm going to draw it. And this sampling distribution requires what we call our true proportion, or our true mean, our true average of the data. Now that average in this case, the true proportion, is 42%, because the problem says that 42% of Americans have type A blood. For us to do a sampling distribution, we have to have a statistic like this. A statistic that we know is true, or as close to accurate and true as humanly possible. I mean, this is information coming from the Red Cross after who knows how much research, right? So we assume this is the true proportion of people with type A blood. So that mean is 42%. So this kind of answers our very first question. If the true proportion of the amount of people in the world with type A blood is 42%, then we should expect 42% of the people who show up at the test to have type A blood, or show up at the blood drive, whatever the situation was, right? Now, if there's 80 people that show up, we can take 42 times 80, figure out how many people that is, or 0.42 times 80, figure out how many people that is. But this mean gives us the expected proportion. Now, the second part of this is where it gets a little bit more intricate, because it says, 42% is the real percentage, but not every data set is going to be exactly like that. Not every data set is going to have the perfect exact mean. Like if you flip a coin 100 times, you know that you're most likely to get 50-50, but are you actually going to get that? Maybe not. So what we need to do is we need to find the standard deviation, or the sampling error, or the sampling deviation, whatever term you like for it, which is found through the equation, the square root of P Q over N. Now I go into this equation in a little more detail in the previous video, but to cut things short, P is the true proportion, the proportion of success, as we may call it. In this case, type A blood is what we're looking at. So the proportion for type A blood is 0.2 or 0.42%. So Q is the proportion of failures, quote unquote, meaning in this case, anything that's not type A blood, right? Like if a person comes in with B, AB, O, whatever it might be, well, that's not what we're looking for. We're looking for type A. So the opposite proportion is our Q value. Since traditionally proportions are going to be written as percentages, as decimals, then Q, it can typically be considered 1 minus P. So if 42% are going to have type A blood, that means 58% are not going to have type A blood. Finally, we have N, and N is the number of people that are participating in whatever we're doing, or the number of trials that are happening. Number of times the coins flip, number of times the people are drawing blood, the number of times that we roll the dice, whatever it may be. In this case, they said 80 people were coming in, so we're going to write that just as so. And then we can go ahead and calculate this. I want to go ahead and grab the calculator here real quick. And we can square root this. We want to make sure we put our numerator in parentheses so that it does not mess up our order of operations at all. Not that it would here, I don't think, but I always like just to be safe. You can see the whole thing's under the square root, and we get 0.055. So the standard deviation, sampling error, sampling deviation, whatever you want to call it, is 0.055. That equates to 5.5%. So in this data set, we know one standard deviation over is 0.055, so we would add that to the 0.42. 0.42 plus 0.055, and find out that one standard deviation over is 47.5%. And one standard deviation over from that is going to be 53%. Now we can also subtract these numbers. One standard deviation on the lower side is going to be at 36.5%. And then one standard deviation below that will be at 31%. This tells us that in 95% of the cases where we have people come in to donate blood, that we will have between 31 and 53% of the people with type A blood. 68% of the time we'll have between 36.5% and 47.5%. And the average amount of people, the most common amount of people, will be 42. So again, this is a sampling distribution. This is how we find the standard deviation. And to actually answer the questions on number 5 right here, let me get this on here. What's the expected proportion of people who are type A? Well, that would be 42%. We already covered that. What's the standard deviation of the type A proportion found at such drives? Well, that's 0.055 or 5.5% is the standard deviation. We're going to do one more of these in this video. Number 6 says about 12% of children are nearsighted. A school district will be testing the vision of 170 incoming kindergarten children. What proportion of these kids should we expect to be nearsighted? Well, that first question is pretty straightforward. If 12% of students are nationwide, then we should expect 12% of these students to also be nearsighted. So we just know right off the bat, A is 12%. B, however, we need to find that standard deviation. Again, to do that, we use the equation we talked about a little bit ago. The square root of PQ over N. P, the true proportion of people who fit the criteria of what we're looking at. That would be 12% or 0.12. Q, the number of people, or sorry, not the number, but the percentage of people that do not fit it. That would be 100, not 170. What was I thinking? That's the number of kids they're doing. 88%, so 0.88. And then the number of trials they are doing, or the number of students they are checking on, was 170. So we can type into our calculator here the square root of 0.12 times 0.88 divided by 170. And we find out that the standard deviation is 0.025 or about 2.5%. All right, so that's how we solve these problems. What you guys can try out is number 7 here. Number 7 says let's construct a sampling model or sampling distribution. So it looks just like this. This is what we're drawing. And it wants us to take some of the information we knew about, actually, looking at number 7, that's what we already did. Sorry, I thought that was a new data set, but that refers to problem number 5 that we just completed. So we'll actually talk about number 7 here. So it just says to construct this sampling model, which we did. Now what we did was we took the mean and we went out 2 standard deviations to the 95th percentile portion. And it says to go all the way to the 99.7 percentile. Now that would really just mean going out 1 more standard deviation on either side. So we would end up with 99.7% of the data if we subtracted 5.5% from each side, on the lower side and the upper side. All right. You don't have anything you got to try out today. I changed my mind on that. I just wanted us to go over these couple of problems. Tomorrow we'll probably go over another 1 or 2, and I'll probably have a couple problems that you can try out individually if you would like in that video. If you have any questions about this, feel free to email me. Otherwise, see you guys tomorrow.